This is a basic blender. You can find this machine in most kitchens across America and many throughout the world. Most people just use this product for its intended use, namely, to blend food together. They do this without giving much thought into how it works. In this video, we're going to change that. We will go over how the blender is held together before we get into how electricity is turned on and moves through the device, how the electrical motor spins and expels its excess heat, and finally, how the blades of the blender actually break down and combine all the foods put into it. Wink wink, this probably does not happen how you think it does. This is the blender base. It holds everything together. It's split into the upper housing and the lower housing. The two housings are held together by these 4 screws, which can be accessed by a long neck screwdriver. The motor is screwed onto the upper housing via grommets using flange round head screws. These screws have a large load bearing capability because they are able to spread the preload of the screw over a larger area than a regular screw. This prevents the screw from pulling through the material under load, which is especially helpful when what you're screwing into is a rubber grommet. The grommets are then in turn attached to the motor mount, which has these 4 screws affixing it to the stationary part of the motor called the stator. The stator is made up of lots of different parts that we will not get into in this video. I do want to point out though, that these 2 long screws hold all the various parts of the stator together. The whole motor hangs down into the hollow cylinder of the lower housing. The motor is held up by the motor mount and 3 grommets because the harmonic vibrations of a hanging motor spinning at 17,000 to 30,000 revolutions per minute can be quite intense, especially one that is even slightly unbalanced, as this harmonic simulation shows. Let's say the motor is spinning at 17,000 revolutions per minute. That translates to 283 Hertz. The definition of Hertz is cycles per second, so this motor at this speed is spinning at 283 revolutions per second. At that speed, the simulation shows that the motor is vibrating back and forth about 6,000 of an inch. Its vibration is primarily damped by the 3 grommets it's hanging from, thus protecting the blender from its motor. Moving up from the engine, the container kit, which is made up of everything now shown, is needed to hold and blend food together. The container is not held onto the base by anything but gravity. The blender's user simply grabs onto the handle and lifts it off the base when ready to pour. This whole section of the container kit is called the cutter assembly. This is the collar. Its job is to interact with the base and align itself with these grooves so that the user of the blender does not need to think about the position of the container when put on the blender. It can be just put down and the necessary alignment happens practically automatically. There are 2 clutches. The bottom is connected to the motor and is called the motor clutch. The top is connected to the blades and is called the blades clutch. These 2 clutches are used in conjunction to transfer power from the motor to the blades. When the container is lifted off the base, even if the motor is currently spinning, the 2 clutches will disengage and the blades will stop spinning. These are the blades. They are connected to the blade clutch by this drive shaft. The blades stay centered because of the mounting plate, which, helped by very small gaskets not shown, also keeps liquid from falling into the base. Interacting with the outer diameter of the mounting plate is the jar. The jar is the food and liquid container. It can be made of glass, plastic, or metal. Blender jars come in many different shapes and sizes just like blenders do. This is not a one-size-fits-all type of product. There is a rubber seal glued to the mounting plate which also prevents liquid from flowing out of the jar. This is the lid and filler cap. I am sure everyone listening to this video who has ever used a blender knows that if the lid and filler cap are not securely placed on the top of the jar when the blender is turned on, that there is a strong possibility that what is inside the jar will soon be everywhere else. This explosive mess shows the power of the spinning blades and the importance of the lid and filler cap. Now that we know how the motor is mounted to the base and how it interacts with the blades causing them to spin, let's turn our attention to the control panel, which is how the blender is turned on. The control panel is held to this bracket by these two screws, which in turn is held to the upper housing by these three screws. If we come over to the 5 buttons of the control panel, this is where everything starts. This button turns the device off. When you push one of these 4 buttons, the blender will turn on and the blades will start to spin. These are the 2 pulse buttons. When one of these 2 buttons are pushed, the blender will only stay on as long as the button is being pushed down. When these 2 buttons are pushed, the button can be released and the blender will stay on. The off button or either of the pulse buttons will turn off the blender when one of the 2 permanently on buttons have been pressed. So why do some buttons stay pressed down after being released and others do not? Let's see how the mechanism behind the buttons works. Each button has a spring that wants to push the button back up. Each button also has a small metal plate called a contact plate. This plate is precisely machined to keep the button in place and helps turn the blender on when the button is pressed down. Inside the control panel box, there is another longer metal plate, also precisely machined, called the slider plate. As the button is pressed, the slider plate is pushed to the left and compresses a small spring which pushes it back into its original position when the pressed button is released. At least, that is how 3 of the buttons work. The 2 permanently on buttons work a little differently. When one of these 2 buttons are pushed, the slider plate moves to the left in the exact same way, but push the button down far enough and it clicks into place. The slider plate has these cutouts in strategic positions that keep the button from going back up. The stiffness of the button spring pushing up and the slider plate pushing right keeps the slider plate and button stationary. The button and slider plate are essentially in a standoff which keeps the blender turned on. The only way to turn the blender off at this point is to push one of the buttons without a notch on the slider plate, like the off button. The compress button is now free to move back up into its off position, turning the blender off as well. Now let's see what pressing a button does. Here we're going to show a SOLIDWORKS Nonlinear Simulation of the button being pressed, and how it interacts with the rest of the mechanism. As you can see, pressing a control button moves this plastic push bar known as the plunger down, because it is connected to the button's contact plate. Moving the plunger down makes it come in contact with this small, thin copper connecting strip called a contact, pushing it backwards. If the contact is pushed back far enough, it will touch another much longer copper strip spanning the length of the control panel, called the bus bar. Each of the 4 buttons that turns the blender on has one of these contact strips, and they each can come in contact with the bus bar. When one of the contacts touch the bus bar, the motor will turn on because the electrical circuit of the blender has been closed. When the button is released, the contact springs back to its original position and the motor will turn off because the electrical circuit is now open. After a button has been pressed and the electrical circuit is closed, let's investigate the pathway that electricity takes through the device. It starts at the plug, which has 2 copper wires. Electricity will start moving in one direction along one of these wires and the opposite direction in the other. When the electricity reaches the end of the plug, it is transferred to a different wire in this connector housing that holds several wires all intertwined and clamped down inside of it. The electricity goes up the new wire until it travels through a contact and then through the bus bar. It then travels along this black wire, which is connected by a simple zip tie to one of two stationary copper coils called a field coil. The electricity will travel through the field coil into another small wire and eventually reach the brush motor kit. The electrical motor used in this blender is called a brush motor because it uses a graphite brush to conduct electricity into the blender's motor. This brush is held in place by the brush housing and this spring behind the brush. The brush can be pushed back, but when released, it will be pushed forward quickly by the spring. This spring keeps the brush constantly up against the spinning portion of the electric motor called the rotor. The part of the rotor that the brush touches is called the commutator, which is made up of multiple copper segments that are separated and insulated from each other. Tied to each copper segment are copper windings known as the motor's armature windings. These windings connect one copper segment on one side of the commutator to the copper segment on the other side. There are two brushes, both touching their respective sections of the commutator 180 degrees from each other, and both part of the electrical circuit. With electricity flowing through the armature windings, an electromagnet is formed. We are not going to get into how the electromagnet is formed in this video, but suffice it to say, when the magnet first takes shape in this first set of armature windings, it spins the motor, which spinning motion causes the brushes to come in contact with the next set of copper segments, pushing the rotor a little farther, spinning it a bit more, and on it goes. As we continue on the electricity's path, it leaves the rotor along this short wire, through the second field coil on the opposite side, and then through this white wire, which is connected to the second copper wire of the plug in this second connector housing, allowing the electricity to move along the opposite side it entered, thus completing the circuit. Everything we've been over this far in this video, all of these complex mechanisms, have one purpose: to spin the blender blades, which spinning is obviously powered by the electrical motor, and the spinning creates a lot of heat. This heat is expelled by the engine itself because a fan is bolted directly onto the bottom of the rotor, so it spins at the same speed the engine spins. As this fan spins, it creates a powerful vortex of air in the hollow cylinder that the engine hangs down in. As you can see, cold air is pulled into the base through these slots at the base of the cylinder and these slots at the side of the lower housing. This air is moved around in the base and especially vortexes around the engine, which is the main heat source in the blender. This vortex gives the air plenty of time to suck heat from the engine, then move out of the base through these slots, taking the heat with it, allowing more cold air to be sucked in. Towards the beginning of this video, I told you the ability of the blender to pulverize solid food into a liquid slush possibly does not happen the way you might think. I know before I started researching blenders, I thought the blending process was due to the sharpness of the blades spinning so fast that they cut the food particles over and over again until they were so small they became a slushy. This cutting process is how the solid food is broken up into smaller chunks at first, but it is not the end of the story. Blenders have two other processes that break up the food into much smaller bits than the sharpness of the blades could ever account for. The first of the two processes is that the blades of the blender spin so quickly that they form a vortex of spinning liquid that is sucked down the middle of the jar and flung out and up along the hard walls of the jar at such a velocity that it pulverizes the food. The second process is called cavitation. Cavitation happens when bubbles form in a liquid that is not at its normal boiling point. It is essentially boiling not because it is too hot, but because the pressure in the liquid is so low that it forms bubbles at low temperatures. This cavitation process happens in a blender because the blades of the blender spin so quickly that it increases the localized speed of the liquid in this area, making a low pressure zone. Here we see a plot of how fast the local liquid is moving around the blades. The liquid boils at ambient temperatures in this zone, creating small steam bubbles. These bubbles cannot be shown in flow simulation, but we can see where the low pressure zone forms on and around the blades, as well as see plots of density and volume fraction of vapor. The density plot shows the area forms bubbles because steam bubbles have a much lower density than liquid water. And the volume fraction of vapor plot shows bubbles forming in the same areas because this plot shows a percentage of how much of the liquid is taken up by vapor versus fluid, 0 being pure liquid and 1 being only vapor. You can see the red areas of the blades show a 50-50 split between bubbles and liquid in this area. These bubbles move around in the liquid like everything else in the blender jar. As a bubble moves from a low pressure zone to a high pressure zone, the low pressure bubble implodes. Each of these implosions create powerful local shock waves that further break down the food particles in the surrounding liquid. Now you know the various parts of a basic blender and how they all fit and work together to get the blender's blades to spin so fast that they can break solid food into smoothie. So the next time you press one of your blender's buttons, you might stop and ponder on all these complex mechanisms and think, maybe this blender is not so basic after all.